What if everything you see around you is not really solid? Look at your hand for a moment. It feels solid. The table in front of you feels solid. The earth beneath your feet feels completely real and stable. But modern physics tells us something strange, something almost unbelievable. When scientists zoom deeper and deeper into matter, they discover that reality becomes less and less solid. First we find molecules, then atoms. Inside atoms we find electrons and protons. Inside those we discover even smaller particles called quarks. For a long time, physicists believed these tiny particles were the final building blocks of the universe. Tiny points of matter, the smallest things that could possibly exist. But then an astonishing idea appeared. What if those particles are not actually points at all? What if instead every particle in the universe is actually a tiny vibrating string? This is the core idea behind string theory. According to this theory, the universe is built from unimaginably small strings of energy. These strings are so tiny that they are billions of times smaller than an atom. In fact, they are so small that even our most powerful machines cannot see them. But here is where the idea becomes truly fascinating. These strings do not just exist, they vibrate. And the way they vibrate determines what kind of particle they become. Think about a musical instrument for a moment. Imagine a guitar. When a guitarist plucks a string, the vibration of that string creates a sound. Change the vibration slightly, and you get a completely different note. The same string, different vibration and different sound. String theory suggests something very similar is happening in the universe. One vibration of a string might create an electron. Another vibration might create a quark. Another vibration might create a photon, a particle of light. In other words, every particle we see in nature could simply be a different vibration of the same fundamental string. If this idea is true, it means the entire universe is like a giant cosmic symphony. Matter, energy, light, gravity, everything could be different notes played by tiny vibrating strings hidden deep inside reality. But this raises a huge question. Where did this strange idea come from? Why did physicists start thinking that the universe might be made of strings instead of particles? And what problem were they trying to solve when this theory first appeared? Because the story of string theory does not begin with certainty. It begins with confusion, a mystery, and one of the biggest problems in modern physics. And to understand that mystery, we need to go back in time, to a moment when scientists realized that the laws of the universe did not fully agree with each other. The story of string theory does not begin with confidence. It begins with a problem. In the early 20th century, physics was revolutionized by two powerful theories. On one side, there was quantum mechanics, a theory that explained the strange and unpredictable behavior of tiny particles. It showed us a world where particles could exist in multiple states at once, where uncertainty was built into the fabric of reality. On the other side, there was Einstein's theory of general relativity, a theory that explained gravity, space, and time on a cosmic scale. It described how massive objects bend space-time, creating what we experience as gravity. Individually, both theories were incredibly successful. Quantum mechanics could predict particle behavior with astonishing accuracy. General relativity could explain the motion of planets, stars, and even black holes. But there was a problem. When scientists tried to combine these two theories into a single framework, everything broke down. The equations stopped making sense. Predictions became infinite. The math simply refused to cooperate. It was as if the universe was speaking two different languages, one for the very small and one for the very large, and physicists were desperate to find a way to unify them. This search became one of the greatest challenges in modern science. A theory of everything, a single idea that could explain all forces of nature, became the ultimate goal. Then in the late 1960s, something unexpected happened. Physicists were studying the behavior of subatomic particles during high-energy collisions. They were trying to understand the strong nuclear force, the force that holds atomic nuclei together. But the data they were getting was strange. The patterns did not match traditional particle models. Instead, the results looked more like vibrations, almost as if the particles were not points, but tiny oscillating objects. At first, this idea was not taken seriously. The early version of the theory had problems. In fact, it predicted a particle that didn't seem to exist at the time. Because of this, many scientists abandoned the idea and moved on. For a while, string theory was almost forgotten, but then something surprising happened. Years later, physicists revisited the equations and realized that the problematic particle they had predicted might actually be something incredible. It behaved exactly like a particle that could carry gravity, a particle that physicists had been searching for, the graviton. Suddenly, the theory that once seemed wrong started to look revolutionary, because if string theory naturally includes gravity, then it might be the missing link, the bridge between quantum mechanics and general relativity. The idea that was once ignored was now impossible to overlook. But this raised an even deeper question. If the universe is made of tiny vibrating strings, then where exactly do these strings exist? Because the answer is far stranger than anyone expected. If the universe is made of tiny vibrating strings, then where do these strings actually exist? At first, scientists assumed the answer was simple. The strings exist in the same universe we see around us, in 3 dimensions of space and 1 dimension of time. But when physicists began to study the mathematics of string theory more deeply, something didn't add up. The equations refused to work properly. They produced inconsistencies, contradictions, impossible results. It was as if the theory itself was incomplete. But then came a shocking realization. The problem was not with the strings. The problem was with our understanding of space. According to the mathematics of string theory, the universe does not have just 3 dimensions of space. It has much more. In fact, for the equations to work perfectly, the universe needs a total of 10 dimensions, sometimes even 11, depending on the version of the theory. This idea sounds impossible at first. We only see 3 dimensions: length, width, and height. We can move forward and backward, left and right, up and down. So where are these extra dimensions hiding? Why can't we see them? To understand this, imagine a simple example. Picture a thin wire stretched out in front of you. From a distance, it looks like a one-dimensional line. You can only move forward or backward along it. But now imagine you are a tiny ant walking on that wire. Suddenly, the situation changes. The ant can move forward and backward, but also around the wire in small circular paths. To the ant, the wire is not one-dimensional. It has an extra hidden dimension, curled up so tightly that it is almost invisible from far away. String theory suggests that our universe might work in the same way. The extra dimensions are not missing, they are simply hidden, curled up at incredibly small scales, far smaller than atoms, far smaller than anything we can directly observe. These tiny, compact dimensions could exist at every single point in space, silently shaping the behavior of the strings. And here's the most fascinating part. The way these extra dimensions are shaped could determine how strings vibrate. And if string vibrations create particles, then the shape of these hidden dimensions could determine the entire structure of reality. Every particle, every force, every law of physics, all of it might depend on invisible dimensions that we cannot see. But this idea raises a deeper mystery. If extra dimensions control the behavior of the universe, then what exactly are these dimensions made of? And how do they influence forces like gravity? Because when we talk about gravity in string theory, we are stepping into one of the strangest ideas ever proposed in physics. Among all the forces in the universe, gravity is the strangest one. It is the force that keeps your feet on the ground, that holds the planets in orbit, that shapes galaxies and bends the fabric of space-time itself. And yet, compared to other forces, gravity is incredibly weak. Think about this. A small magnet in your hand can easily lift a paperclip, overcoming the gravitational pull of the entire Earth. That should not be possible. Why is gravity so weak? This question has puzzled scientists for decades, and surprisingly, string theory offers a very unusual answer. According to the theory, gravity might not actually be weak. It only appears weak because it is leaking into other dimensions. Yes, other dimensions. Remember those hidden dimensions we talked about? String theory suggests that while most forces are confined to our familiar three-dimensional space, gravity is different. Gravity can move beyond our visible universe into the extra dimensions that we cannot see. To imagine this, think of our universe as a flat surface, like a sheet of paper. All the particles, all the forces like electromagnetism, they are stuck on this sheet. They cannot leave it, but gravity is not limited in the same way. Gravity can travel off the sheet, spreading into the higher dimensions around it. So when we try to measure gravity in our world, we only feel a small part of its true strength. The rest of it is hidden, flowing through dimensions beyond our perception. This idea could explain why gravity seems so much weaker than other forces. But string theory goes even further. It predicts the existence of a special particle, one that carries gravity. This particle is called the graviton. Unlike other particles, the graviton would not be confined to our visible dimensions. It would be free to move through the entire higher dimensional space. If this is true, then gravity is not just a force. It is a messenger, traveling between dimensions, connecting different layers of reality. But this leads to an even bigger question. If gravity can move through hidden dimensions, could there be entire universes hidden there as well? Universes that we cannot see, I cannot touch, but that exist right beside us. Because once we start thinking about extra dimensions in this way, we are no longer talking about just one universe. We are stepping into the possibility of many. What if our universe is not the only one? It sounds like science fiction. But within the framework of string theory, this idea becomes a serious possibility. To understand this, we need to rethink what we mean by the universe. We usually imagine the universe as everything that exists, all space, all time, all matter, all energy. But string theory suggests something far more complex. It suggests that our universe might be just one layer, floating inside a much larger reality. Physicists call this idea a brane. Think of a brane as a kind of surface like a sheet, existing in a higher dimensional space. Our entire universe, galaxies, stars, planets, even you, could be living on one of these branes. Everything we see and interact with might be stuck on this surface. Light, particles, forces, all confined to our brain. But remember what we learned earlier. Gravity is different. Gravity might not be trapped like everything else. It could move freely between branes, through the extra dimensions. Now imagine this. If one brane exists, there could be others. Multiple universes, each on their own brane, floating parallel to ours. Close or incredibly close, but completely invisible to us. You could be standing right next to another universe and never know it exists. This idea is often connected to what scientists call the multiverse. A reality where countless universes exist side by side, each with its own laws of physics, its own particles, its own story. Some universes might be almost identical to ours. Others could be completely different, with strange physics, different dimensions, or even no life at all. But here's where things become even more interesting. If these branes exist, they might not always stay separate. In some models of string theory, branes can move. They can stretch, vibrate, and even collide. And if two massive universes collide, the energy released would be unimaginable. Some scientists have even suggested that such a collision could explain the origin of our universe itself. What we call the Big Bang might actually be the result of two branes crashing into each other. If that idea is true, then the beginning of our universe was not the beginning of everything. It was just one event in a much larger cosmic system. But this raises a deeper mystery. If there are many universes, what determines the laws of each one? Why does our universe have the exact properties needed for stars, planets, and life? Because in string theory, The answer might lie in something even more fundamental than universes themselves. If there are many universes, each with different laws of physics, then a deeper question begins to emerge. What actually decides those laws? Why does our universe have the exact forces, the exact particles, the exact balance needed for stars, planets, and life to exist? Why not something completely different? Inside string theory, the answer may lie in something almost invisible, yet incredibly powerful: the shape of the hidden dimensions. Earlier we explored the idea that extra dimensions exist, curled up at incredibly small scales. But these dimensions are not just empty space. They have structure, they have geometry, they have shape, and that shape might control everything. Imagine a musical instrument again, a flute, for example. The sound it produces depends on its structure, its length, its holes, its design. Change the shape of the flute, and you change the sound it creates. In string theory, the extra dimensions act like that instrument, and the strings are like vibrations moving through it. If the shape of these hidden dimensions changes, the vibrations of the strings change. And if the vibrations change and the particles change, that means the entire identity of a universe, its particles, its forces, its physical laws, could be determined by the geometry of these tiny, hidden dimensions. Scientists often describe these shapes as incredibly complex, folded in ways that are difficult to even imagine. At scales far smaller than atoms, these dimensions could be twisting, curling, and looping in precise patterns. Each possible shape creates a different version of physics, a different kind of universe. This leads to a breathtaking idea. There may not be just one correct version of reality. There could be an enormous number of possible realities, each defined by a different configuration of hidden dimensions. Some physicists believe the number of these possible configurations could be unimaginably large, a vast landscape of universes, each with its own unique laws. In one universe, gravity might be stronger. In another, atoms might not even form. In another, time itself could behave differently. And out of all these possibilities, we find ourselves in a universe that just happens to support life. But this creates a new mystery. If so many universes are possible, why does ours exist the way it does? Is it just a coincidence? Or is there a deeper reason, a hidden principle guiding the structure of reality? Because to answer that question, we need to explore one of the most controversial ideas connected to string theory. If the universe could have been different, then why is it exactly the way it is? Why do the laws of physics seem perfectly balanced for life to exist? If gravity were slightly stronger, stars would burn out too quickly. If it were weaker, stars might never form at all. If the forces inside atoms were even slightly different, matter as we know it would not exist. No planets, no chemistry, no life, and yet here we are. Inside string theory, this question becomes even more serious, because the theory suggests that many different universes could exist, each with its own set of physical laws. So why this one? One possible answer is known as the anthropic principle. It sounds complicated, but the idea is simple. We observe this universe the way it is, because only this kind of universe allows observers like us to exist. In other words, we are not in a special universe. We are simply in a universe where life is possible. Imagine a vast collection of universes, millions, billions, perhaps infinitely many, each one slightly different. Most of them would be completely empty, lifeless, chaotic, unstable. But just a few, it would have the right conditions for stars to form, for planets to exist, or for life to emerge. And naturally, those are the universes where someone can ask the question. This idea changes how we think about reality. Instead of asking, why is the universe designed for life? We ask, could we exist in any universe where life is impossible? The answer is no. So perhaps there is no deep design, no hidden intention, just a vast range of possibilities. And we happen to be in one that works. But not everyone is satisfied with this explanation. Some scientists argue that it feels incomplete. It does not truly explain why the laws are the way they are. It only explains why we observe them, and that leads to a deeper search, a search for a fundamental principle, a rule, a law, that determines everything from the beginning. Because if string theory is correct, then somewhere beneath all these possibilities, there must be a structure, a hidden logic that defines reality itself. And to uncover that logic, physicists turn toward one of the most ambitious ideas ever proposed, the search for a single unified theory that can explain everything in existence. For centuries, science has followed a simple dream, to find one rule, one principle that explains everything, a single framework where all forces, all particles, all laws of nature come together as one. This idea is often called the theory of everything, and within modern physics, string theory is one of the strongest candidates for that role. But to understand why, we need to look at the forces that shape our universe. There are four fundamental forces in nature. The electromagnetic force, responsible for light, electricity, and magnetism. The strong nuclear force, holding atomic nuclei together. The weak nuclear force, responsible for radioactive decay. And gravity, the force that shapes planets, stars, and galaxies. For decades, physicists have been trying to unify these forces, and they have made progress. The electromagnetic force and the weak force were successfully combined into a single framework. This was a major breakthrough. There are also theories that attempt to unify the strong force with them, but gravity remains separate. It refuses to fit into the quantum world. Whenever scientists try to describe gravity using quantum mechanics, the equations collapse into infinities. It is like trying to combine two pieces of a puzzle that almost fit, but not quite. This is where string theory becomes so powerful. Instead of treating particles as points, it replaces them with tiny vibrating strings. And within this framework, something remarkable happens. All forces begin to emerge from the same fundamental object, the same string. Different vibrations of the string give rise to different particles, and different particles create different forces. Even gravity appears naturally in the equations, not as an added feature, but as an unavoidable result. This is something no other theory has achieved in the same way. For the first time, physicists had a model where all forces could, in principle, be unified. A single underlying structure, creating everything we observe. It was a breathtaking possibility, but there was a problem. Actually, many problems. Because while string theory is mathematically elegant, it is also incredibly difficult to test. The strings are far too small to observe directly. The extra dimensions are hidden beyond our current technology. And without experimental evidence, a theory remains just that, a theory. So the question becomes unavoidable. Is string theory truly describing reality? Or is it just a beautiful idea, a mathematical dream that we cannot prove? Because to answer that, scientists need something more than equations. They need evidence. And finding that evidence is one of the greatest challenges in modern physics. A theory can be beautiful. It can be elegant, powerful, even convincing. But in science, one thing matters above all else: proof. No matter how impressive an idea may seem, without evidence it cannot be accepted as reality. And this is where string theory faces its greatest challenge. Testing it. The problem begins with size. String theory suggests that the fundamental building blocks of the universe are tiny vibrating strings, far smaller than anything we have ever observed. To detect something that small, we would need an enormous amount of energy, far beyond what our current technology can produce. Even the most powerful machines ever built, like the Large Hadron Collider, are not enough to directly observe these strings. They operate at incredibly high energies, but still nowhere near the scale where strings would become visible. This creates a serious limitation. If we cannot see the strings, how can we prove they exist? So scientists began searching for indirect evidence, clues, signals, small effects that might reveal the presence of hidden dimensions or string-like behavior. One idea involves extra dimensions. If additional dimensions exist, they might influence how particles behave at high energies. For example, gravity might become stronger at very small distances, or particles might suddenly behave in unexpected ways. Physicists carefully study collision data, looking for anything unusual. So far, nothing definitive has been found. Another possibility involves cosmic observations. The early universe, just after the Big Bang, was an environment of extreme energy, conditions where the effects of string theory might have been more visible. Scientists study cosmic background radiation, gravitational waves, and large-scale structures in the universe, searching for patterns that cannot be explained by standard physics alone. Again, the results are intriguing, but not conclusive. This is the frustration. String theory offers answers to some of the deepest questions in physics, but it remains just out of reach of experimental confirmation. And this leads to a serious debate in the scientific community. Some physicists believe the theory is too far removed from observation. They argue that without testable predictions, it risks becoming more like philosophy than science. Others disagree. They believe that just because we cannot test it today does not mean it is wrong. After all, many scientific ideas were once impossible to test until technology caught up. So the question remains open. Are we simply not advanced enough yet to see the deeper structure of reality? Or are we chasing an idea that may never be proven? Because if string theory is correct, then somewhere in the universe there must be signs, subtle, hidden, waiting to be discovered, and finding those signs could change our understanding of reality forever. At this point, string theory sounds like a single idea, a bold attempt to explain everything using tiny vibrating strings. But the deeper scientists explored string theory, the more complicated it became. Because there isn't just one version of string theory, there are many. In fact, at one stage, physicists discovered something surprising. There were 5 different consistent versions of the theory. 5 mathematical frameworks, all describing strings, but in slightly different ways. Each version had its own rules, its own structure, its own interpretation of how reality works. This created confusion. How can there be multiple theories of everything? Which one is correct? Or worse, what if none of them are? For a while, it seemed like the dream of a unified theory was slipping away again. But then something remarkable happened. Scientists began to notice deep connections between these different versions. They realized that these theories were not completely separate. They were related, like different perspectives of the same underlying truth. Through a set of powerful mathematical relationships, physicists showed that one version of the theory could transform into another. It was as if the 5 theories were different faces of a single hidden structure. This realization changed everything. Instead of competing theories, they became pieces of a larger puzzle, a puzzle pointing towards something even deeper. This deeper framework was later called M-theory, a theory that does not just include strings, but also higher dimensional objects, extending beyond simple one-dimensional vibrations. It suggested that our understanding of reality was still incomplete, that strings might not be the final answer, but part of something even bigger. And here's where things become even more fascinating. If multiple versions of the theory exist, and all are connected, then reality itself might not have a single fixed description. It could be flexible, dependent on perspective and on scale, on how we choose to observe it. The universe might not be defined by one simple rule, but by a network of interconnected principles, each one revealing a different aspect of the same truth. But this raises a powerful question. If all these versions are connected, what is the true underlying structure behind them? What is the ultimate form of reality that gives rise to all these different theories? Because answering that question may take us beyond strings, beyond dimensions, into a level of physics that we are only beginning to imagine. At first, the idea seems simple. Everything in the universe is made of tiny vibrating strings, but as scientists explored string theory more deeply, they began to realize something unexpected. Strings might not be the final answer. They might just be the beginning. Because in the mathematical structure of the theory, new objects started to appear. Not just one-dimensional strings, but higher dimensional objects as well. These objects are called branes. A string is one-dimensional, like a line, But a brain can exist in multiple dimensions. A two-dimensional brain would be like a surface. A three-dimensional brain would be like a volume. And in advanced versions of the theory, there could be brains with many dimensions, far beyond anything we can visualize. This idea changes everything, because if such objects exist, then our universe itself could be one of them. A vast three-dimensional brain, floating inside a higher dimensional space. Everything we experience, matter, light, forces, could be confined to this brain. We would live our entire lives without ever realizing that a larger reality exists beyond it. But here's where things become even more intriguing. Strings do not just exist on their own. They can attach to brains. Some strings might be open, with endpoints attached to a brain. Others might be closed, forming loops that can move freely through higher dimensions. This distinction is important because it could explain something we discussed earlier. Why most forces are confined to our universe, while gravity is not. Open strings attached to our brain could represent particles like electrons and quarks. They are trapped, unable to leave our universe. But closed strings could move beyond the brain. They could travel through extra dimensions, carrying forces like gravity across the higher dimensional space. This idea connects everything together: strings, brains, dimensions, forces, all part of a single interconnected structure. But it also leads to a deeper realization. If our universe is just one brain, then there could be others. Other brains, other universes, coexisting within the same higher dimensional space. And if these brains interact even slightly, the consequences could be extraordinary. Tiny interactions, subtle vibrations, could leave detectable traces in our universe, signals from beyond our own reality. But this raises a powerful question. If these higher dimensional objects are real, can we ever detect them? Can we find evidence that our universe is part of something much larger? Because answering that question would not just change physics. It would completely redefine our place in existence. If our universe is just one layer, floating inside a higher dimensional reality, then a natural question arises. Can we ever detect what lies beyond it? Inside string theory, this is not just a philosophical idea. It becomes a scientific challenge, because if extra dimensions and brains are real, they should leave behind traces. Not direct images, not clear signals, but subtle effects, small disturbances, hidden patterns, tiny deviations from what we expect. And scientists are searching for exactly that. One possibility comes from gravity. If gravity can move through extra dimensions, then at very small distances it might behave differently. Instead of following the usual rules, it could become stronger than expected. Physicists design extremely sensitive experiments, trying to measure gravity at microscopic scales, looking for even the slightest change. So far, the results remain consistent with known physics. But the search continues. Another possibility lies in high-energy particle collisions. When particles smash together at enormous speeds, they recreate conditions similar to the early universe. In such extreme environments, the hidden dimensions might briefly reveal themselves. Some theories suggest that energy could leak into extra dimensions during these collisions. If that happens, it would appear as missing energy, a gap in the data, a signal that something has escaped our visible universe. Scientists carefully analyze collision results, searching for these missing pieces. But once again, no clear evidence has been confirmed. There is also a more cosmic approach. Instead of looking in laboratories, scientists look at the universe itself. They study ancient light, patterns in cosmic radiation, the structure of galaxy, trying to find signs that cannot be explained by our current understanding alone. Because if extra dimensions influence the early universe, their effects might still be visible today, encoded in the largest structures we can observe. But here's the challenge. These signals, if they exist, are incredibly faint, hidden beneath layers of noise, masked by other physical processes. Finding them is like trying to hear a whisper in the middle of a storm. And yet, the possibility remains that one day, a small anomaly and a tiny inconsistency could reveal something extraordinary. Evidence that our universe is not alone. Evidence that reality extends far beyond what we can see. But until that moment arrives, string theory remains balanced between two worlds, a theory of immense potential and a mystery still waiting to be solved. And as the search continues, a deeper question begins to take shape. What if the universe is not just built from strings, but from something even more fundamental? So far we have imagined the universe as being built from strings, tiny vibrating strands of energy, shaping everything we see. But what if even that picture is incomplete? What if strings themselves are not truly fundamental? As physicists pushed deeper into string theory, they began to question the very foundation of the theory. Because every time we try to describe reality, we assume something is already there: space, time, dimensions. We treat them as the stage on which everything else exists. But what if the stage itself is not fundamental? What if space and time are not basic ingredients of the universe, but something that emerges from a deeper level of reality? This idea is both strange and powerful. Imagine a digital image on a screen. From a distance, it looks smooth and continuous, but when you zoom in, you begin to see pixels, tiny units, combining together to create the full picture. Now imagine going even deeper. What if space itself is like that image, not continuous, but built from something smaller, something discrete, something more fundamental than dimensions themselves? Some physicists believe that strings might actually arise from an even deeper structure, a kind of underlying fabric, where the concepts of space and time do not exist in the way we understand them. In this deeper layer, there may be no distance, no direction, no before or after. Only relationships, connections between fundamental elements forming a network, a structure, a hidden architecture of reality. And from this structure, space and time could emerge, just like a pattern emerging from pixels. In this view, strings are not the final building blocks. They are patterns, excitations, vibrations appearing within a deeper system, a system we are only beginning to explore. This idea changes everything, because it suggests that reality is not made of things in the traditional sense. It may be made of information, or interactions, or something we do not yet have the language to describe. And if that is true, then our entire understanding of physics is just a surface layer, a simplified picture of something far more complex beneath it. But this leads to an even bigger question. If space and time are not fundamental, then what is? What is the true nature of reality when we strip away everything we think we know? Because answering that question may require a completely new way of thinking. A new kind of physics, beyond particles, beyond strings, beyond dimensions. We are used to thinking of space and time as permanent, unchanging, the stage on which everything happens. You exist somewhere at some moment, and everything around you follows that structure. But what if that idea is wrong? As physicists continued exploring string theory, they were forced to consider something deeply unsettling. What if space and time are not fundamental at all? What if they are illusions? Not illusions in the sense that they don't exist, but illusions in the sense that they are not the deepest level of reality. To understand this, imagine a movie playing on a screen. You see motion, action, time passing. But in reality, the movie is just a sequence of still frames. Your brain connects them, creating the experience of continuous movement. Now think about time. What if time works in a similar way? What if what we experience as a smooth flow is actually emerging from something more basic, something not bound by before and after, and space? Imagine a map on your phone. You can zoom in and out, move across it freely. But the map itself is made of data, stored in a completely different form. The space you see is just a representation. In some modern approaches to physics, space itself might work like that. Not a fundamental reality, but something that emerges from deeper relationships, from connections, from interactions, from a hidden structure beneath everything. In this view, distance is not truly distance. It is a measure of how strongly things are connected. Two objects may seem far apart, but at a deeper level, they could be closely linked. This idea leads to a radical possibility. That reality is not built on geometry, but on relationships, not on space, but on connection. And from these connections, space and time arise as secondary effects, a kind of projection of something more fundamental. This is one of the most profound shifts in modern physics, because it suggests that everything we experience, location, movement, time, is part of a higher-level description, not the base layer. And if that is true, then the universe is far stranger than we ever imagined. But it also opens a new door. If space and time can emerge, then maybe they can also be understood, controlled, even redefined. And that leads us to a powerful and mysterious idea. What if reality itself is more like information than physical substance? If space and time are not fundamental, then what is? What is the deepest layer of reality, beneath everything we see? As physicists continued to explore ideas connected to string theory, a new possibility began to emerge, a possibility that sounds simple, but changes everything. What if the universe is not made of matter, but of information? At first, this idea feels abstract. Information does not seem like something physical. You cannot hold it. You cannot see it directly. And yet everything around you depends on it. Think about a book. The paper and ink are physical, but the meaning of the book, the story, is information. Without that information, the book is just blank pages. Now think about a computer. Inside it, everything is just electrical signals, zeros and ones. But those signals create images, videos, entire worlds. What we experience is not the raw data, but the interpretation of that data. Some physicists believe reality may work in a similar way. At the deepest level, the universe might be built from fundamental units of information, not particles, not strings, but bits of information interacting, evolving, creating patterns. And from those patterns, everything else emerges: matter, energy, and space, time. All of it could be a kind of output of an underlying informational structure. In this view, a particle is not just a tiny object. It is a packet of information, a specific pattern within a larger system. Even space itself could be encoded information, a network of connections, defining how different parts of reality relate to each other. And time? Time could be the process by which this information changes, a sequence of updates like frames in a computation. This idea has deep implications, because if reality is made of information, then the universe is not just a physical system. It is something closer to a computation, a process, constantly evolving, following rules that generate everything we observe. But this raises an even deeper question. If the universe is based on information, where is this information stored? What is the system running this process? And is it possible that what we experience as reality is only a surface layer of something far more complex beneath it? Because to explore that idea, we have to step into one of the most fascinating concepts in modern physics, a concept that suggests reality itself might be like a projection. What if everything you see is not the full reality? What if the universe is more like a projection, a surface-level image of something deeper? As ideas connected to string theory continued to evolve, physicists began exploring a concept that feels almost unreal: the holographic principle. To understand this, imagine a hologram, a flat surface that can store a three-dimensional image. Even though the surface is two-dimensional, it contains all the information needed to describe a 3D object. Now apply this idea to the universe. What if our three-dimensional world is actually encoded on a two-dimensional boundary? What if everything inside our universe is a projection of information stored somewhere else? This is not just science fiction. It comes from deep studies of black holes. When physicists analyzed black holes, they discovered something strange. The amount of information a black hole can contain does not depend on its volume. It depends on its surface area. That means all the information about everything that falls into a black hole is somehow stored on its boundary. This idea led to a powerful realization. If information in a black hole is stored on a surface, maybe the same is true for the entire universe. Maybe reality itself is holographic. In this view, the world you experience, the space, objects, motion, is like an image projected from a deeper layer of information, a lower dimensional structure, encoding a higher dimensional reality. This changes the way we think about existence, because it suggests that what we perceive is not the source of reality, but a representation, a projection of something more fundamental. And here's where it connects back. String theory provides a mathematical framework where this idea can actually work. In certain models, a theory of gravity in one space can be equivalent to a theory without gravity on its boundary. Two different descriptions of the same underlying reality. It is like having two languages telling the same story, one in higher dimensions, one in lower dimensions. Both correct, both complete but deeply different. This duality is one of the most surprising discoveries in modern physics, because it suggests that reality can be described in completely different ways and still be the same. But this raises a powerful question. If our universe is a projection, then what is the original? What is the deeper layer where the true information exists? Because answering that question may take us even further into the limits of knowledge itself.
The deeper we go into reality, the stranger it becomes. We started with particles, then moved to strings, then to dimensions, then to information, and even the idea that the universe might be a projection. But now a new question begins to emerge. Is there a limit to what we can truly understand? As physicists explore ideas connected to string theory, they are not just discovering new theories. They are also discovering boundaries, limits, not just of technology, but of knowledge itself. Think about this. To test a theory, we need experiments. We need energy, tools, measurements. But what if the scale we need to explore is far beyond anything we can ever build? What if the fundamental structure of reality exists at a level that is permanently out of reach? Not just today, but forever? This creates a serious challenge, because science depends on observation. If something cannot be observed, cannot be tested, can it ever truly be confirmed? Some physicists argue that this is where string theory struggles. It is mathematically powerful, beautiful, consistent, but incredibly difficult to test. And without direct evidence, we may never know for certain if it describes reality. But the limitation is not just experimental. It might also be conceptual. The human brain evolved to understand everyday experiences, objects, motion, the cause and effect. But the deeper layers of reality may not follow those intuitive patterns. Concepts like extra dimensions, emergent space, and holographic projections, these are not just difficult, they are fundamentally outside our natural way of thinking. It is like trying to explain color to someone who has never seen, or trying to imagine a new direction beyond up, down, left, right, forward, and backward. There may be aspects of reality that we can describe mathematically, but never truly visualize, never fully feel or understand in a human sense. And yet, we keep trying, because that is what science does. It pushes against the limits. It explores the unknown, even when the answers seem unreachable. But this leads to a deeper thought. Maybe the goal is not to know everything. Maybe the goal is to get closer, step by step, understanding more with each discovery. Because even if we cannot reach the final answer, the journey itself reveals something profound. It shows us that reality is far richer, far deeper than we ever imagined. But there is still one final question. So after everything we have explored, strings, dimensions, information, projections, is string theory actually correct? Or is it just one path among many possible ways to understand the universe?
After everything we have explored, one question remains. Is this the truth? Is string theory the final answer to reality? At first glance, it feels like it could be. It offers a way to unify all forces. It naturally includes gravity. It connects particles, dimensions, and even information into a single framework. It is elegant, it is powerful, it is beautiful. But in science, beauty is not enough. A theory must be correct. and that requires evidence. So far, string theory has not been experimentally confirmed. No direct observation of strings, no clear detection of extra dimensions, no definitive proof that its predictions match reality. This does not mean the theory is wrong, but it does mean we cannot yet say it is right. And this has created a divide among physicists. Some believe string theory is our best hope. They argue that its mathematical consistency and its ability to unify physics make it too strong to ignore. They believe that with future technology, we may eventually find the evidence we need. Others are more skeptical. They argue that a theory that cannot be tested may not belong to physics at all, that it risks becoming speculation, a beautiful idea without proof. Instead, they explore alternative approaches, different paths, different frameworks are trying to solve the same deep problems in completely different ways. This is how science moves forward, not with certainty, but with possibilities, multiple ideas competing, evolving, each one pushing us closer to a deeper understanding. And maybe the truth is not simple. Maybe there is no single final theory. Maybe reality is too complex to be captured by one idea alone. Or maybe string theory is just one piece of a much larger puzzle that we have not fully discovered yet. But regardless of the outcome, its impact is undeniable. It has changed the way we think about space, time, matter, and reality itself. It has forced us to ask deeper questions, to explore beyond what we can see. And in doing so, it has taken us closer to the edge of knowledge. But before we end this journey, there is one final step. Not about equations, not about dimensions, but about you. Because the biggest question is not just about the universe. It is about our place within it. After everything we have explored, strings, dimensions, hidden realities, we arrive at something unexpected. You, not as a scientist, not as an observer, but as a part of the universe itself. Because if string theory is even partially true, then you are not separate from this story. You are made of it. Every atom in your body, every particle, every tiny vibration could be part of the same underlying structure that shapes the entire cosmos. The same fundamental strings that may exist inside distant stars, inside galaxies, inside the fabric of space-time, could also exist inside you. This changes the way we see ourselves. You are not just living in the universe. You are an expression of it. A temporary pattern, formed by deeper rules emerging from a hidden layer of reality. Think about that for a moment. The universe, after billions of years of evolution, has created something that can look back and ask questions about itself. Through you, the universe becomes aware. It observes, it thinks, it wonders, and perhaps that is one of the most profound aspects of existence. Not just what the universe is made of, but that it can be understood, even partially down from within. And yet, we are still at the beginning. We have theories, ideas, mathematical structures, but so much remains unknown. We do not yet know if strings truly exist. We do not know if extra dimensions are real. We do not know if reality is ultimately made of information, or something even deeper. But we are searching, and that search matters, because every step forward, every new idea, every question we dare to ask, brings us closer to understanding the nature of reality. Not completely, but more than before. And maybe that is enough. Because the story of the universe is not just about answers. It is about curiosity. It is about the desire to explore and to understand, to go beyond what we know. And that journey is still unfolding. But even now, standing at the edge of knowledge, one thing is clear. This is not the end of the story. It is only the beginning. In fact, it may have never truly begun, because everything we have explored, from particles to strings and from dimensions to information, is still only a glimpse, a partial view of something far greater. Inside the framework of string theory, we have seen a universe that is not simple, not fixed, not fully understood, a universe where reality is layered, where what we see is only the surface, where deeper structures, hidden dimensions, and unseen connections shape everything around us. But here is the truth. Science is not a finished book. It is a process, an ongoing journey, driven by questions. Every answer we find leads to new mysteries. Every discovery opens new doors. And sometimes, the more we learn, the more we realize how much we do not know. Think about where we started. Solid objects, simple ideas, a clear and understandable world. And now, reality feels different, less certain, more complex, almost alive with hidden possibilities. And yet, this uncertainty is not a weakness, it is a strength, because it pushes us forward. It forces us to explore, to imagine, to challenge our assumptions. String theory may or may not be correct, but its true power is not just in its answers. It is in the questions it creates. Questions about reality, about existence, and about the nature of everything. And those questions will continue to guide science for years, decades, perhaps centuries. So where does that leave us? Right here, at the edge of knowledge, looking into the unknown, with tools that are still growing, ideas that are still forming, and a universe that is still revealing itself. And maybe that is exactly where we are meant to be, not at the end, but in the middle of discovery. Because the universe is not just something to observe, it is something to explore. And that exploration is far from over. In fact, it has only just begun. The journey continues, but now the question shifts. What comes next? If string theory cannot yet be proven, if its predictions remain beyond our reach, then how do we move forward? The answer lies in the future, in new ideas, new technologies, new ways of thinking, because science has always evolved. There was a time when atoms were just a theory, a time when black holes were considered impossible, a time when even the idea of space bending felt absurd. And yet, with time, observation, and innovation, those ideas became part of our understanding of reality. String theory may be following the same path. Right now it sits at the edge of what we can test, but that edge is not fixed. It moves as our tools improve, as experiments become more powerful, as observations become more precise. We may begin to see hints that were invisible before. Future particle accelerators, far more powerful than anything we have today, could probe deeper into the structure of matter. New detectors might capture signals we currently cannot even measure. Observations of the universe, from gravitational waves to cosmic radiation, may reveal patterns that point toward hidden dimensions. Even advances in mathematics could unlock new ways to test the theory indirectly. Because sometimes the key to understanding reality is not just better machines, but better ideas. And here is something important. Even if string theory is not the final answer, the work done in exploring it is not wasted. Every equation and every model, every attempt to understand it, adds to our knowledge. It sharpens our thinking. It pushes physics forward. And sometimes, the path that does not lead directly to the answer still leads us closer to it. So the future of this journey is not uncertain in a negative way. It is open, full of possibilities. Maybe string theory will be proven. Maybe it will evolve into something else. Maybe a completely new idea will take its place. But whatever happens, the search will continue, because the desire to understand reality is not something that stops, it grows. And as long as we keep asking questions, as long as we keep exploring, the story of the universe will keep unfolding. And somewhere in that unfolding, we may finally discover what lies at the very foundation of existence. The search for truth is never simple. It is not a straight line, not a single path leading directly to the answer. It is a field of ideas, competing, evolving, challenging each other. And string theory is not alone in this journey. While many physicists support it, others explore completely different approaches, different ways to understand gravity, space, time, and the fundamental nature of reality. Some theories try to rebuild physics from the ground up, without strings, without extra dimensions. Others focus on quantum geometry, suggesting that space itself is made of tiny, discrete units. Each approach has its strength, its weaknesses, its own vision of what reality might be. And this diversity is not a problem, it is necessary. Because when ideas compete, they become stronger. They are tested, refined, pushed to their limits. Weak ideas fade away. Stronger ideas survive, evolve, and move closer to truth. This is how science progresses, not through agreement, but through questioning. Even the most promising theory must face doubt, must face criticism, must prove itself against alternatives. And string theory is no exception. Some scientists argue that it is too complex, too flexible, able to adapt to almost any result. Others believe that its mathematical depth is exactly what makes it powerful. That beneath its complexity, there is a deeper simplicity waiting to be understood. This tension creates movement. It keeps the field alive. Because without challenges, a theory can become stagnant. But with competition, it is forced to grow. And here is something important to understand. Science is not about belief. It is not about choosing a theory because it feels right. It is about evidence, about logic as consistency, and the ability to explain reality better than anything else. So right now, we are in a phase of exploration. Multiple ideas, multiple possibilities, all moving toward the same goal. To understand what the universe truly is. And maybe the final answer will not come from one idea alone. It may come from a combination, the merging and of different approaches into something entirely new. Because the deeper we go, the more we realize that reality is not simple, and understanding it may require more than one way of thinking. After everything we have explored, from the smallest possible scales to the largest structures in the universe, we arrive at a moment of reflection. A moment to ask, what does all of this really mean? Throughout this journey, string theory has guided us through some of the deepest ideas in modern physics. It suggested that reality may not be built from solid particles, but from tiny vibrating strings. It introduced the possibility of hidden dimensions, curled up beyond our perception. It opened the door to multiple universes, coexisting beyond what we can see. And it challenged our understanding of space, time, and even reality itself. But now we must face the truth. As powerful as this theory is, it is still incomplete. It is not yet proven. It is not yet confirmed by direct evidence. It exists in a space between imagination and reality. And that is not a weakness. It is the nature of discovery. Because every great idea in science once existed in that same uncertain space. A place where questions are stronger than answers. So what can we say with confidence? We can say that string theory is one of the most ambitious attempts to unify the laws of nature. We can say that it provides a framework where gravity, particles, and forces can emerge from a single underlying structure. We can say that it has pushed physics to explore deeper, to question more, to think beyond traditional boundaries. But we must also say this: we do not yet know if it is correct, and that honesty is what makes science powerful. Because science does not claim certainty without evidence, it remains open, flexible, ready to change when new discoveries appear. So what about the future? What might happen next? There are many possibilities. It is possible that future experiments will finally detect signs of extra dimensions or indirect evidence of strings. It is possible that new technologies will allow us to explore energies far beyond what we can reach today. It is possible that mathematical breakthroughs will reveal testable predictions that confirm the theory. But it is also possible that string theory is not the final answer, that it is only a step towards something deeper, a foundation that leads to a more complete understanding, a theory that will evolve into or even be replaced by something we have not yet imagined. And that possibility is just as important, because progress in science does not depend on being right immediately. It depends on moving forward, exploring ideas, testing them, learning from them, and getting closer to the truth with each step. So in the end, string theory is not just a theory, it is a journey, a way of thinking that pushes us to look beyond the visible and to question the nature of reality itself. And perhaps that is its greatest achievement. Not that it has given us all the answers, but that it has shown us how deep the questions really go. And as we stand here at the edge of what we know, one thing is certain. The universe is far more complex, far more mysterious, and far more beautiful than we ever imagined. And the search to understand it will continue.